Yep. Hello, everybody. Welcome to the session, and welcome to Vegas for those from outside here, like myself. So let me introduce myself. I'm Richard Freeman. I'm based in London, and I work for JustGiving. And today's session is about serverless data pipelines, event-driven ETL, and stream processing. Just a little bit about my background. So I have a PhD in machine learning and natural language processing. Back in the day when being a data scientist wasn't actually as sexy as nowadays. So I got that in Manchester University back in the UK. After that, I got a job in a consultancy, Capgemini, so I've got 6 years experience moving from a developer up to a solutions architect. Then I worked for various organizations before joining JustGiving around 3 years ago. So this is what we're going to be covering today in the session. So we're going to have a recap on some of the AWS managed services. Then we're going to be talking about the different challenges that we faced and the requirements that we needed to meet in terms of big data. So these were the initial requirements about 3 years ago that we were looking to move a lot of the processes and data science forward. Then I'll be giving a brief summary on the existing event-driven data pipelines that exist on the market. And then we'll be covering our data platform. And from that, actually, we'll be abstracting that down into 5 different patterns that you can implement within your organization. I'm going to conclude on some recommendations around serverless technology and the best practices that you can use within your organization. So first, a very brief recap on some of the AWS services. And before I do this, I just want to get a show of hands for how many people have used serverless technology or Lambdas. Great, lots of people. How many people have used Redshift? Yeah, good show of hands. And finally, how many people have an automated data pipeline to actually load data into Redshift? Okay, there's fewer hands, but obviously people are interested, so we're going to cover that today. So you've probably heard some of this already, but I'm going to reiterate it for others that aren't aware of it. So on the left, we've got AWS S3, Amazon S3, which is a distributed web store for objects. So it's immutable, so once you add an object, it's persisted until it gets removed. It's highly scalable. It supports almost petabytes of data or unlimited amounts of data, anything you can throw at it almost. And it's a very cheap way of doing it, as you only pay for the actual storage that you consume on S3 itself. It supports encryption. You can obviously compress those files and to reduce the storage cost. AWS Lambda, so obviously for those who are using serverless technology, you probably used it before. We started using it a few years ago already, and I've written some blogs about it. It allows you to run specific code based on some trigger. So the trigger could either be based on some events that are added into Kinesis streams, or a specific object is added to an S3 bucket, and that will trigger the Lambda function. Within the Lambda, you can actually run any of the analytics code or any type of code that you want to do. It also supports the Amazon API gateway, which is, you can think of it as a REST endpoint that you can call, and that will invoke a Lambda in a serverless way. The Lambda would do some computation or some lookup, and then return the results through your REST API. The beauty is you only pay for the amount of code, the amount of time that your code executes down to the 100 milliseconds. It's highly scalable, highly available. Again, that's all managed for you by AWS. Amazon Redshift is a massively parallel processing data warehouse, which allows you to run SQL and CSQL on top of large amounts of data. It's highly optimized to actually load data from S3 and Dynamo and Elastic MapReduce. It's got extensive security. It supports roles, encryption at rest, and encryption in transit. It also has, this is one of the very good benefits, actually, why I like it. It's got JDBC and ODBC connectivity, supports anti-SQL, and also there's a Postgres interface, actually, so you can communicate using any of the tools that exist on the market, including vendor tools for BI, so you're not tied to a specific MPP. So on the right, we've got Amazon Elastic MapReduce, which allows you to do either batch processing at scale or real-time analytics. A lot of people will be talking about Spark, and this is where Amazon supports out of the box the open source platforms, installs all of that on the EMR cluster, and you have Spark up and running in 10 minutes, basically. It supports both long and transient running clusters. So you could imagine you've got a huge ETL job. You need to process a petabyte of data. You can spin up 1,000 machines just for the duration of that job and then shut them all down. The beauty for me is the spot instances. This is where you can actually bid for spare capacity in Amazon at a very low price. So you can spin up 1,000 nodes again at a reduced cost rather than the more expensive on-demand prices. So the other three I want to talk about that are relevant to the talk is Amazon Kinesis. So we started off with Amazon Kinesis Streams, and this is a way of ingesting a lot of data very fast and making it available for other services. So you could think of thousands of or millions of IoT devices pushing in sensor data into Kinesis Streams, and that's what it's built for. In JustGiving, we use it for ingesting web analytics data. If you pipe the data out of Kinesis, you can actually use Amazon Kinesis Analytics and run SQL commands on the stream of data. And that's all integrated already. Amazon Kinesis Firehose is an endpoint, you could think of it, where you actually push a lot of events. Those will get buffered in memory and then written out to S3. And they can also be loaded into Redshift or Amazon Elasticsearch service. Okay, so now we've covered some of the background, just for those who weren't aware of it. So I'm going to be talking about our challenges and requirements at JustGiving. I'm going to first introduce JustGiving. So we are a tech for good company. We work in event-based fundraising, in the charity space, and crowdfunding for good. So these are for good causes. We are the #1 platform for online social giving in the world. And this is based on the amount of money that we've raised, which is $4.2 billion in donation to date. So yeah, that's a huge amount when you think about $4.2 billion helping for those in needs, helping the animals, helping your local communities. And we've got a massive user base also. So we've got 28.5 million users who actually transacted on the platform in 196 countries. And our platform supports 27,000 good causes, which are charities or crowdfunding for good projects. And what we like to do is apply data science also. So my background's a PhD in machine learning. So obviously, I've got an interest in data science, and so do understanding how people donate. And almost our motto, I would say, is to ensure that no good cause goes unfunded. And we found that in order to do this in a data scientific way, we actually need to provide content that is highly relevant to the user and that is very engaging for them, relevant. And we found it was difficult at the start to do that. We have a lot of data. We need to understand almost how that works. So what we found is we created a graph of relationships between the users. So people who create a page to raise money for a specific cause, who are actually running for a marathon, for example, and people who actually sponsor them. And actually creating what we call a give graph, which is a relationship between nodes. So we have about 91 million nodes. So these are the users, the charities, and also a decomposition of the charity, which means, for example, if it's Dogs Trust in the UK, we decompose it into an animal charity, specifically dogs, and in specific locations around the country. So we're actually decomposing the whole essence of what the charity does. So those are nodes. And interrelationship between all those nodes, we have 500 million relationships. And that helps you understand and provide more engaging content, we found. And that actually integrates with Facebook, and it is the largest giving graph in the world. Just taking a step back, so this is what your journey would look like if you go into JustGiving. So here we have an example of one of our products, which is a fundraising page. So this is Sophie's Royal Parks half marathon. So she's running for a charity that's really close to her heart, which is around the mental health. So she wants to raise money. She set a target, a value that colleagues, friends, and families are going to sponsor her, and that she hopes to reach. So you can see there's a target. There's also updates that she provides at the bottom. She's able to share this on social media, Facebook, Twitter, or by email. And you can see a list of the supporters on the right. And actually, behind all of this, there's a lot of data science that we do. So we actually know based on the estimates, based on your past history with the platform, how much we think you're going to be able to raise. So again, this is maximizing the revenue for that specific charity. We also have different mechanisms to show more engaging content to the specific users. So you can see different products. So behind the scenes, we're capturing a lot of the analytics data. So these are page views, different impressions, different clicks for share, for example, on Facebook. And that allows us to analyze all of that and to run various tests. So you can think of that as a fundraising product. We have various features that we release, such as the updates. That's a fairly recent feature, for example. So our requirements were at the time that our SQL Server data warehouse wasn't able to cope with long-running queries and the complexity that queries required for data scientists, such as the graph queries that we talked about earlier. In addition, we were receiving more and more data sources, and we needed a way to ingest that data and to run processes on it. So if you think about the clickstream data, that's one source. So we're getting clickstream at user level. We're also getting API data, so from the likes of Facebook, SurveyMonkey, ExactTarget, and other news feeds and data sources. In addition, we're getting log data, so this is the app log or the web server logs coming in, as well as what I talked about earlier, the behavioral data. How do users actually interact with the specific products? What do they like? If we make recommendations, do they actually click on those recommendations? So we're capturing a lot more data sources. Our data warehouse wasn't able to cope. So we were looking for other solutions almost. On the other side, we're also looking for a way to add new data sources very easily and create a platform that allows us to create a pipeline, an ETL pipeline or ELT pipeline for data preparation. And you can see I've put a very simplified view of what we have in our automated pipeline. So we have the data ingestion that we talked about, the data preparation, as well as the machine learning, graph processing, and NLP pipelines. In addition, we are providing streaming analytics. So this allows us to ingest data, analyze it in real time, for example, the page view data, and provide some metrics back to the users. On the right, you can see this is more the outcome. So we have a great platform that works, and the data-driven approach that we wanted to use was to actually measure and make insight available to end users, as well as provide predictions based on all the data that we have. Recommendations are also important. So as I said, we're recommending a target value. We're recommending default values to the user. And those are all based dynamically on our data science models. So I'm just going to go over some of the keynotes, some of the key points that exist in the existing big data ETL platforms. So we talked about some of this already, but I just want to reiterate some of it. So there is the concept of an automated data pipeline where you want to automate the execution of your machine learning algorithms. There's always a way of querying that data and manipulating it efficiently. That's why a data pipeline is required. If you're doing ad hoc analysis as a data scientist, it doesn't matter too much. When you want to automate and productionize the reporting, you need to have this automation in place. There's always some sort of data schema, some models around the actual data, the specific columns or the specific key pairs that is always available. Typically, how data pipelines work, they support either a scheduled job, so it runs at a specific time, for example, at midnight every day, or we have triggered jobs based on some other types of events. So this could be a file is added to S3, for example. There's always a requirement for monitoring and for looking at any failures and reloading that data almost continuously. And typically what I found is looking at all the open source, looking at the other vendor products, there's always some sort of concept of a workflow or a directed acyclic graph, or DAGs for short, which I'll show you next. So the DAGs in ETL, I believe, this is my view, can go very complex. Imagine you have 1,000 nodes and you end up with huge, almost flow of dependencies. Sometimes, it depends on which products you look at. These are actually hand-drawn graphically. There are abstractions where you abstract different layers and you call different layers, but again, there's a lot of dependency in the actual flow. Also, I found it very difficult if you're moving from one workflow engine or one DAG to another, it's not obvious. You need to redraw it, you need to recreate it. Again, there's such a variety of workflows out there, but this is a typical pattern in the market right now. So if in the green boxes we're introducing a change to one of the tables, for example, or the data formats, that would have to get propagated in workflow. So you'd have to go and edit it and change everything. Also, what I found is a lot of the integration that exists right now is point-to-point integration. So this is where if you make one change, that gets added into Redshift directly. So there's no, you need to actually modify your workflow if you want to load it into a different cluster. Also, they don't tend to support very well spinning up different EMR clusters dynamically, loading the data in, and then spinning them down. So I found some of the solutions, and they don't necessarily integrate directly with Spark in an advanced way to create the machine learning pipelines. It's also complex to reload. So some vendors, products, open source products, have a way, a dashboard of viewing and reloading. But again, that introduces some complexity. So I'd say in general, if you're doing any big data analytics, batch analytics or batch loading ETL is very easy. Incremental is a lot harder. You need to take into account duplicates. So obviously you don't want duplicates. You don't want to drop any data. So there's always this incremental concept. Usually they use different types of user interfaces, and you need to spin up a cluster of machines almost to create your big data pipeline. So now I'm just going to talk about the event-driven data platform in JustGiving. So at JustGiving, we created our in-house data analytics platform, which we call Raven, which stands for Reporting, Analytics, Visualization, Experimental Networks. So rather than use DAGs or workflows, we're actually using event-driven architecture and serverless pipelines. Event-driven architecture is probably more familiar amongst yourselves, so people who are developers and architects, and maybe less for the traditional ETL, BI type people. It relies on messaging, queues, publish, subscribe mechanisms. So probably developers who use enterprise service buses will be aware of what I'm talking about in terms of messaging, being more dynamic, responding to events, sending a message, and decoupling almost one system from another. So it's all about loose coupling. And we also separate the data, which is stored in S3, from all the computing. So rather than doing, for example, an ETL in Redshift, we're actually doing the ETL in Spark or other services and then loading it in. It supports the scalable ETL, machine learning, natural language processing via Spark, and graph processing. At the end, it allows us to consume the raw data in Redshift or in Spark, data blocks, which is a join between all the data sources, such as the clickstream, the transactional data, and other data sources, and provide insight and dashboard metrics. So maybe for the more technical audience, this is an overview of the platform. So you can see on the top left, we have the web analytics. So I'll decompose this into 3 types of web analytics, which I think every company should have. So we capture the client-side analytics. So we're currently using Kissmetrics to do that. For the server side, we're using Kinesis streams. So each of our microservices, microsites actually sends analytics events to Kinesis streams. And we also have Logstash. So that's the web logs, the app logs, where we capture that data. We use clickstream data in Kissmetrics and Kinesis streams because we have the detail of the user. So we're not getting aggregates. We're actually getting the specific user. This is their journey on the website or the mobile app. So we actually have an understanding of the actions that they're taking. In terms of mini surveys, we're using Qualaroo currently. So those will pop up within a specific context. So they're very context sensitive, a very small survey that appears at the bottom that you can dismiss if you're not interested. We also have, you see on the middle left, we have different API integrations. So integrate with ExactTarget, SurveyMonkey, Twitter, other open sources, news feeds. And that we have a process to actually pull all that data from their APIs. The third pattern that we have is actually to pull data from a data warehouse. So we pull facts and dimensions, OLTP. Rather than doing a pull, we're doing a push actually to not overwhelm our data warehouse currently. And that's done all through the next layer, the data integration, where we have different processes to read all that data, to process it, to run the ETL jobs. And we're going to drill down into that detail for yourselves afterwards. That's all done in a secure way. So we're using roles as part of the IAM. And we're also using what we'll see, how we do the event-driven using queues. In addition, we've got a Lambda function also to do some of the lightweight ETL, which we'll cover in great depth. The data storage, so we have Redshift. Everything, when we started off, everything was centered around Redshift. So the whole orchestration of loading data, running the ETL into Redshift, Redshift-centric. And then we started to scale out even further. We wanted to use the Spot instances, so we started using Amazon Elastic MapReduce, as well as introducing more of the machine learning at scale. And you can see on the right, so what our data scientists would do is use R and Python. And they found it really, really useful to connect to Redshift straight, because you can load the data straight into data frames. And you've got it all available, already cleaned up, all the pre-processing that the data science community don't always talk about, but they spend maybe 80% of the time preparing the data, shaping the data, cleansing the data, enriching the data. And they don't need to do that anymore, which is great. Other integration points that we have is Tableau. So you run automated reports. Tableau allows our product managers and maybe the non-IT people to actually visualize and graph the results. So these could be aggregate counts. It could be the specific page views, for example, for all the fundraising pages, understanding a new product release. Any of the A/B testing is available in there. In addition, our machine learning engineers also use Spark and EMR. And that's a great way, I think, to spin up a cluster during office hours, maybe. You can run all your ETL jobs on that automatically and your machine learning, and then shut it down. We're mastering the data as part of the data lake within S3. What's funny is we also have SQL Server taking aggregates out of Redshift, so it almost loops back because we're able to support the hundreds of terabyte scale. Last one. So we've got AWS Lambda also for streaming analytics, and we're going to talk about this as part of the patterns. So from this, the data integration layer is what I'm going to be covering in a bit more depth. And we've derived 5 different patterns that you can use in your organization. So the first you need to understand how we view event-driven ETL and a way of loading the data on multiple clusters. So actually, I've got a simplified example here. So we've got an external API, and we're fetching data using a microservice. So you can think of this triggered every hour, maybe, and you're fetching a subset of the data, an incremental subset. You're writing that data into an S3 bucket, and then sending a message to a specific topic. That topic has 2 subscribers. We've got 2 queues where it gets forwarded on, it gets broadcast on, and then we have a loader. So we've got a microservice that actually initiates a load that's polling the queue, and then loads that into Redshift. And you can see if you want to add another cluster, so here we've got Analytics 1, Analytics 2. If you want to add Analytics 3, the only thing you need to do is add another microservice and put a subscriber to the topic. And we've totally decoupled almost the extraction of the data, the downloading of the data right into S3 from the actual loading into Redshift. This also could be used using Spark and other processes. We could have Hive tables on EMR. So the pros are there's a lot of flexibility on the loading, supports incremental load on multiple clusters, multiple environments. You're almost not tied anymore to where it's getting written. And again, it's this concept of separating the storage from the compute, which is really valuable. It's simple to understand, I think, as a pattern. You can see that, for example, just going back, if Redshift is resizing and goes into read-only, for example, or if it's in maintenance mode, then that service will just shut down and wait until Redshift comes back, and the items remain on the queue. So you can actually view the workload almost of Redshift. You can choose to load one message at a time or many. So that's why I find that incremental loads work really well using this system and using messaging. And I think a lot of developers understand this concept. So I'd recommend looking into it more. Basic sequencing can be done within a message. For example, you could load some data and then run some SQL on Redshift. Again, you're decoupling, creating a huge workflow. You're just loading it incrementally, running the processes that you need, and then you're done. The cons are, obviously, if you want to create a huge workflow and your workflow is 1,000 steps, then obviously it's not really meant for that. Also, there wasn't any FIFO support, which is the first in, first out in SQS. But actually, about a week ago, that's been introduced in the US, but not in the EU West yet. So that's no longer an issue. So if you have an order in which you want to load data, you're able to use that functionality in the SQS. Okay, so that pattern of loading was important for the next 5 patterns that we're going to talk about in terms of data pipelines. First pattern, so this is, we're using what we call a cluster-based big data pipeline. This is pattern number 1. So we have all the data already in an S3 bucket. We prepare the incremental load using what we call the content manager. So we know the exact files that have been prepared. We know almost the input folder. And then we're sending a message to an SQS queue, which has the size of the cluster, the target, input, and output folders. And then that message gets read by the Raven EMR job runner, which spins up the EMR cluster, submits almost the specific jobs that you want to do on the data. Once that's executed, and the cluster will shut down, and then that job runner will then send a message onto a topic. And then we talked about the pattern for loading that data. So we'd have a loading process to load that data. We know where these files are because it's part of the metadata of the message. So the pros are it supports Spark jobs, natural language processing. You can actually do your machine learning. So Spark has the machine learning pipeline now, so you can actually sequence specific steps in your machine learning process. And GraphX is also there if you want to run graph analytics at scale on a cluster. Things have improved a lot since previous frameworks, compared to the previous frameworks, I'd say. Now with Spark, things are a lot simpler. And this allows you to run also ETL, the more traditional ETL at scale, so that could be enrichment or any parsing of specific data fields. The Spark jobs itself can contain many steps, but then EMR, you also have a set of steps, so you've got 2 ways almost of sequencing data, which is really good. So the downside of having an EMR cluster, it does take 10 minutes to spin up, and obviously you're paying per hour. So imagine if your huge ETL job takes an hour, 1 minute, then you would actually pay for 2 hours. So obviously that's a limitation. And there's always this concept of how many nodes do I have? Is it better to execute using more nodes to reduce the time? Is it cheaper than having less nodes and taking longer? And sometimes it's actually to have more nodes, and especially with the on-demand, I'd say. Okay, pattern number 2. It's very similar to the first pattern, except that we have streaming data. So you can think of it as our clickstream for page views, for the fundraising pages. And we have a Spark process that actually just reads the Kinesis stream directly. And then this could run any of the machine learning. It could run just simple counts on the actual data itself. And then on a regular schedule, it would write those results out into S3, send a message on the topic, and then that data would get loaded as before using the patterns of the Redshift loader. So the pros are the process we can stream in parallel. This is a fault-tolerant way of processing the data. We benefit already out of the box from a huge open source community in Spark for streaming analytics. A lot of the machine learning already works on that. So we've got things like the streaming k-means. You can actually analyze clusters on the fly using that and use Python, Scala, Java for that. So it's a great way of doing it. You've got a huge community behind it. You've got EMR spun up, supported by Amazon. It's real-time analytics pipeline, so you can also, anything you can do on the EMR cluster allows you to get the analytics out very fast almost, and you can adjust all of that. Downside are, it's always on, so the cluster's got to be always on because the data's always coming in, so you can't turn it off. So you've got this dilemma almost. Do I create a big cluster? Do I resize it based on the amount of data that's added, that's streaming in? So at peak hours on your website, do you actually make the cluster bigger? Do you downsize it? Or do you leave it constant or more expensive? That's not out of the box, actually, so you need to think about that. When you have some of this code deployed on a streaming platform and you want to swap it out because you want to change how you count the events, that's not a straightforward process. And you'll see on blogs they talk about this also. So you need to think about how you checkpoint the existing data so that you do not double count or you do not undercount. So that's not a straightforward thing to do on Spark. So now I'm going to talk a bit about the serverless. I've got 3 more patterns to cover. I think this covers quite a broad range, so you'll be very interested. So just going back to the serverless concepts, so this allows us to run machines or run our code based on some trigger. So the trigger could be a file gets dropped into S3, or specific records are written to Kinesis streams. So, and then these records are actually passed on to the Lambda function as micro batches, where you can actually process them in parallel. And all the auto-scaling, everything's done for you. There's no maintenance. It's almost just deploying the code, and everything works. So you can't remote onto the box. It's a lot simpler even than containers, I'll say. It also scales with capacity, and it's very, very cheap. So you only pay in 100 millisecond increments rather than per hour for the EC2 instances. It's highly secure also, as it supports the IAM roles. So a role could be, for example, to actually read from Kinesis streams, but not write to the Kinesis streams. And you could allow it, basically in that way, lock down the resources. So very secure, highly scalable, no maintenance. So this is the first pattern. I'd say there are scenarios where actually people talk about big data, but sometimes you have small data. So you have lots of files that arrive sometimes, and you don't necessarily want to spin up a cluster or have a machine running on all the time. So as the file gets added, you can have a trigger which is an event source that you provide in the Lambda function to say if an object is checked in, is added to S3, then trigger this Lambda function. The Lambda, in this case, will load the data in memory, process, and run the ETL. So this could be, for example, a very simple transformation of a URL, extracting the domain name, extracting specific patterns within the URL, and then pushing those results out in a JSON format, for example, into S3. And then following the same pattern as earlier, we just send a message onto a specific topic for further processes to actually load that data in, so into Redshift or into a Spark cluster or Hive table. In addition, what's interesting, you can actually also scan S3 for all those files using a client and then send messages via a topic to the Lambda. So each Lambda will be invoked for each file almost. So again, the pros are it supports both the batch and the incremental process. It's very useful for small files, infrequently added files, ones where you don't want to spin up a huge cluster or have a machine running. It also has the ability to preserve the file name. So those of you who use Spark or the older MapReduce jobs, you know that you end up with part 0, part 1, part 2, part 3, even if you just had one file on the input. This one will preserve the same file on the input and output if you want it to. It's a very good pattern, I think, for projecting specific columns, enriching specific rows, and doing parsing on the fly. And again, you can do this in Node, in Java 8, and in Python. There are some limitations, obviously, to be aware of. So there's 500 megabytes disk on a Lambda and up to 1.5 gigabytes of RAM. And the whole process needs to complete within 5 minutes. Complex joins are a lot harder to do because you're actually invoked with one specific file. It is possible, but I would recommend using other approaches, which I'll talk about afterwards. You may not want one file, an input and output. So, for example, if you have one file added every minute, you may not want to have one file on the output. You may want to aggregate them up almost to make it more easy to actually query. And that's where we use the next pattern, pattern number 4, which I call the serverless streamify file pattern, which allows you to merge many small files that are frequently added into a stream. And then you can query the stream either using some analytics processes or persist it into S3. So that's what I'm showing here. So files are added into S3. That will basically trigger a Lambda. The Lambda will read the file in memory, go for each of the rows, and send them off as records into the Kinesis streams. Or if you want to persist them in memory for fast querying, then you can use DynamoDB, which is a NoSQL store. In addition, you can actually persist millions of files into smaller files using the firehose. So the Lambda function will read all those files, streamify it, and then send those events into Kinesis firehose. The firehose will actually capture up to 128 megabytes and up to 15 minutes of data. And that will be written into S3. And then we have a process. As soon as that file gets written, we can trigger another Lambda function to send an SNS topic for further loading further down the line. So the pros are, this is a way you can support batch and incremental in terms of loading. So if I just go back, so you see at the top, we've got the Amazon SNS topic that triggers the Lambda function. So what you can do is, if you've got lots of files that you want to streamify, you can just scan all of S3 and send one message per object in S3. Send that as part of the topic, and the Lambda functions will execute in parallel, read all the files in parallel, run all of that, and send it into Amazon Kinesis streams. So that's the batch process. The incremental one is when the file just gets added, and that triggers a job. So it's very useful for small and frequently added files. It's a very nice pattern. You've got a serverless way to also use a Lambda to do a transformation, transform lots of files into almost a smaller subset, and use the firehose to actually persist that for further analysis or loading. Cons are, again, there's similar limitations for the Lambda. Again, I would re-architect it if it takes longer or if it's larger files. The firehose also has some limits. So I talked about the 15-minute window and 128 megabytes in buffer. So if one of those gets hit, the file gets written. But at least you're aggregating, up to that level. And I'd say for the MapReduce Spark, 128 is a good number to have. Typically, it doesn't like small files, so actually it's a good way to reduce the size of your files. Complex joins are also possible. They introduce a lot more complexity in the architecture, so I wouldn't recommend it for this specific approach. So next pattern is pattern number 5, which is the serverless streaming analytics and persisting the stream. So if you think about what we talked about earlier, so we had the streaming analytics coming in. So we had our clickstream coming into Kinesis streams or into Dynamo if you want. And then micro batches would actually get sent to the Lambda function. So it would receive all the clickstream data. So that could be the page views, the impressions, the clicks for share on Facebook, or specific scrolling events on the website. So all of that gets received as a micro batch in a Lambda. The Lambda itself, in this case, in this scenario, does a running count. So it actually counts the number of page views and impressions for a specific page and sends those into, at the top, we've got the ways of visualizing the data. So it would send that data into CloudWatch metrics. CloudWatch metrics is probably the first protocol, so where you want to have a serverless way of charting data over time. So it's very simple to send metrics. I've written a blog post about this, so you'll be able to find it. I've got details afterwards. And then you can chart over time. You'll see the page views and the specific events for that. If you want something more external-facing or even internal-facing, again, in a serverless fashion, I'd recommend you create an S3 bucket that acts as a static website. So you can actually run Node.js or JavaScript code to actually chart that data. And the data counts, the counts actually are in DynamoDB. Equally, you can create just a raw table and show the page counts, or expose it via some API. So as an alternative, you can also run using Kinesis analytics. So you can run SQL on your clickstream of data and write those results into the firehose, and that will get written into S3. The Lambda can also write to the firehose, and I've got some code to do that also, part of my blog. So same pattern as number 4. The data gets persisted into S3, and then we have a process where as soon as the file's written, the object is written into S3, we trigger another Lambda function that then sends an SNS message topic to a specific topic that will then propagate onto SQS and then get loaded. So the pros of this approach are we're stream processing without any running cluster. So there's no machines running, actually. Everything is managed by Amazon. You've got freedom also of how you do everything. You can mix and match different parts of this architecture. Using the Lambda and Kinesis analytics, you also benefit from auto-scaling. So again, as more data arrives in your clickstream, there's no need to actually think about how you scale out for that at peak times in traffic. And that's something we've benefited a lot at JustGiving, so actually using this auto-scaling facility without having to worry about this. Especially we get spikes of data sometimes, so think about the Ice Bucket Challenge, for example. no makeup selfie. There's various events that are huge in terms of the traffic volumes, so we need to be able to cope with those. So this is a good thing for other organizations looking at spikes of traffic. So you can actually serve those metrics up using a static website, and the metrics themselves are in DynamoDB. So again, there's a way of querying that really fast, getting the aggregate values out. There's a choice of language also, which is quite important. So you can use Python, SQL, Node.js, and Java 8, so within this process. And the code can be changed without interruption. Do you remember for pattern number 2, I was talking about Spark and swapping one application for another. So if you're changing the way you're counting different events, there's always this checkpointing that you need to do. You need to swap it over very carefully to make sure you don't lose data. Using this pattern, you don't need to worry about that. The Lambda also automatically switches over almost in terms of the micro-batch data that it gets. The cons are, obviously, there's some Lambda limits we talked about, the fire hose, and any complex joins between multiple streams. That's just how it's architected. It's probably not the best pattern for this, and there's alternatives I'll talk about afterwards. So based on these 5 patterns, I'm just going to talk about some of the serverless recommendations and the best practices that you can use in your organization. So this is a table showing when serverless is good and when maybe we could use EMR instead. So pattern number 3, the small data pipeline. So this is where we take one file that isn't added that frequently, and we're parsing it, processing it, running transformation, projecting specific rows. So this is a great pattern for that. Also, when you want to preserve the file names, then this is a good pattern. If you have files that are bigger than 400 megabytes and that take maybe longer than 5 minutes to process, I'd recommend you use Spark on EMR. If you have, so this is one file to one file almost. If you have many files to one file, I'd recommend using Spark also. So if you're doing a complex join, I'd recommend that. But if you think about clickstream, you've got a consistency almost. It's almost when you want to do complex joins. There's other patterns, so Spark would be better. Also not recommended for pattern number 3 to use for merging small files into one. Pattern number 4, so this is where we streamify the file and then merge them into a larger file. So if you have millions of files, you've got this ability to use the fire hose to actually compress the data into smaller amounts. And this is a great way. This is one of the limitations of Spark, where if you have lots of files, it's not as efficient to process. So this is a pattern almost to reduce your data volumes. So if you have files, again, greater than 400 megabytes, or if you want to do complex joins between the streams, I'd recommend using Spark on the right. Pattern number 5, so this is a way of running serverless analytics using Lambda functions and DynamoDB and persisting the stream also further down the line. The streaming analytics actually is the results are persisted in DynamoDB, and those results are then presented in real time on the dashboard using Node.js. I've used in my blog, you'll read about it. I'm using charts.js to do that, and also just drawing out some tables. So you can use almost any of the JavaScript frameworks to actually integrate with DynamoDB. And that's a great way to do it. So if you want to do complex joins, again, that's more of a Spark. So you can see you want to save money. You don't want to pay per hour, per node. There's a serverless pattern that's available for you. So Lambda functions are really good for any transformation at row or event level, for parsing, projecting, enriching, and filtering the data. So you can think of it as a record level like this, and you're doing transformations, adding more columns, rather than downwards. So working with other AWS offerings like S3, SNS, CloudWatch, IAM, it's really well integrated, I'd say. So you benefit from the ecosystem already. So for example, for the triggers, if an object is added to S3, that will trigger a Lambda. SNS triggers Lambdas. Micro batches in Kinesis streams trigger Lambdas also. As I talked about, the IAM roles also. So these are specific policies that can be assigned to the role. For example, where the Lambda function can only read from Kinesis, it's not allowed to write, or it can only write to DynamoDB for the counters, for example. And it supports VPC, actually, so you can totally isolate the Lambda function within the service. They're really good also in terms of packaging, so you can package up all your dependencies and then using command line deploy those in terms of versions, so you can actually version control a lot of that. As I said earlier, the stream also, stream processing using Spark is not easy when you want to swap over the applications. With the Lambda functions, that's fairly straightforward. It will just swap over a different microbatch as they arrive. So it's important to understand some of the limits also of the Lambda. So we talked about some of the memory, the local disk, and the execution time. If you think about real-time analytics, so if you are processing something that takes more than 5 minutes, then it's not going to be real-time anymore. So you need to you need to re-architect that so it's real-time. So I'd say anything less than a minute, maybe. You've also got this concurrency limit, so you need to be aware of, which is per account. Again, that can get increased also if you ask Amazon. Dynamo and Amazon Kinesis also have a different set of shard iterators. So if you need more capacity, you can add more shards to Kinesis. And there's almost one shard is linked to one Lambda, so you need to be aware of that also. But effectively, we've taken all of our production clickstream, we ran it through Lambdas, and we didn't have any issues with that. So again, we talked about the complex joins are harder, so that's more suited for using Spark on EMR. Again, using our pattern number 1. And the reason for that is Spark has more context. It can read everything, anything from S3. Whereas here, we're trying to process just a subset of the data almost as fast in real time. In addition, if you want to use ORC or Parquet, which are the big data formats. So these are columnar formats where the data is compressed, similar to Redshift in some ways, and it allows you to query a specific column. It's very fast. It also supports compression. The actual data is, you've got almost the name of the column, and you have the data type of the column, and whether it's mandatory or not in terms of a field. So that's better done in Spark because it's got access to more of the data. So Lambda recommendations, I'd recommend you create a sandbox environment and load all your production data in that to make sure everything's running smoothly. Think about this deployment. How do you automate the deployment process of your code? Because Lambdas are serverless, it's very easy to deploy the code. The simplest method is to actually log on to production, paste your code in. But obviously, that's not the ops wouldn't be happy with you if you do that. It's also important to use the version control to actually deploy Lambda so you can roll back very quickly. And for me, one of the big things is about reducing that execution time. So you've got that 5 minutes. You want to minimize almost the time that's taken to actually run through the data and do the ETL or the analysis of the data. So I found that minimizing the actual logging, so logging only when you really need it, it sped up the speed of the Lambda. Optimizing codes, so for example, rather than writing every record out, you would batch them up into memory in terms of counters and then write that into Dynamo. There's other optimizations I talk about in my blog posts, so I've got links afterwards for that. So event-driven pipelines. So again, think about how maybe you can move away from workflow for some scenarios or move away from the directed acyclic graphs into more incremental loads. So if you think about clickstream data, it's not something you run overnight. It's arriving all the time, continuously. So you might as well use that data immediately and make it available. Think about using some of the managed services also. They're there. They're highly scalable, highly available, and that's all built in for you with the security and all the Lambda functions for that. The state is not maintained within the Lambda. You can maintain it outside the Lambda, so in DynamoDB, in S3, or in RDS. And often you'll see, if you actually break down a directed acyclic graph, you can probably flatten most of it out. And that's what we found in our organization, especially if you're loading data and then running some SQL after it, straight after it. You're almost simplifying, rather than having this huge workflow that executes every night, a big data pipeline, you can actually run smaller batches of data continuously, incrementally. And that allows you to have the data available in closer to real time. Think about, so this is probably one of the key messages, think about how you can decouple the loading in the ETL, ELT. So ELT is probably the big data term where the schema is on the read rather than creating the schema up front. So if you think about using messaging, you can loosely couple actually all the systems. So the data producer from almost the one that loads the data into other clusters. So you can actually load it into, for example, how we use it in JustGiving. In production, we have 4 different clusters, and each cluster of Redshift has a different purpose. One of them is to serve analytics. The other one is to run really complex queries, the data scientists that really push the cluster to the limits. The other one is purely for graph analytics, so running some of the graph analytics in Redshift. So obviously that one's always computing. And then we have more general Redshift cluster used by the developers and ops when we want to investigate. So you can almost have, you're taking it a level further. You're not just having this massive single cluster. You've got many clusters. And the DR is built in another way around, I'd say, because the data is replicated and loaded on all the clusters, and it's all the same scripts are executing all of them. So the ETL is the same. We benefit from the ability to add new clusters on demand. And equally, if a cluster goes down, I can spin up a cluster, reload all the data purely using messaging, so without running any types of workflows or anything. So think about exceptions also. That's really important. So if an EMR job run fails or a Lambda function fails for some reason, you need to think about how you reload that. So it's important to have notifications to do that and a dashboard. And actually, if there is a failure, what we do is just send a message, and that's it, and it's done. And we don't need to replay any workflow or anything. So I'd recommend you master all your data in S3. So have a single source of truth in S3 and make that available to any of the services that want to run ETL or machine learning at scale. Yeah, we like to think of the EMR clusters, Spark clusters, Hive clusters, Amazon Redshift clusters as disposable, because we have this ability to actually reload any of the data on the fly and incrementally as well as in batch if we need it. Data storage, so this is just more traditional patterns. There are best practices. These are the useful ones. So I have 1 file per file type in terms of the prefix. Use an incremental loading notation. So if you want to load a specific year, month, day, hour, that really helps. If you've got data such as comma separated or tab separated from an external vendor, and that's the only format that they support, or some CSV file for some analyst, for example, it's best to have another file that actually describes the file almost in terms of metadata or some metadata layer to do that. If it's Oracle Parquet, that's actually built into it, so you don't need to worry about that. It's more for those other formats. And stick with one consistent date-time format for all your data, so you know that no matter what you do, everything's in UTC and consistent. Compress and encrypt your data also. So here's some of my blog posts. So I've got one on the compute blog, another one on the big data Amazon blog. I've got a Medium article. We've actually also open sourced some of the code, so it's on github.com/justgiving. So just wrapping up, so today we talked about some of the challenges of the existing data pipelines, and we've proposed an alternative way of doing ETL using event-driven and serverless pipelines. We covered the 5 different patterns that you can implement in your organization. So the first 2 required a cluster, the other 3 actually purely serverless. The recommendations I would say is use serverless where possible and manage services. Think about how also you decouple the loading in the ETL or ELT. So I'd like to thank everybody today. So I hope you find everything useful and you can reuse it in your organization, as well as maybe, if you can, think about the tech for good sector and how you can use those skills in that area. And here are my contact details if you want to connect with me on LinkedIn or drop me an email. Thank you very much for your attention.